at how to do mathematics with an LLM, so ChatGPT in this case. And to do so, I have chosen a result which we proved maybe 10 years ago, and it's well hidden in the literature. So I'm quite certain it does not have active memory of this result. And if not, then this would have altogether different consequences if it has somehow internalized all human mathematical knowledge. So let's assume it doesn't know it directly, and let's see if we can reproduce the result. So the topic is, I have a little diagram. So I have a graph G. Here 7 vertices and some edges between those vertices. For example, there's one edge between 4 and 7 and no edge between 5 and 7. And these edges are undirected, but I give them a random orientation by coin flip. So for each edge, I'm flipping a coin, a fair coin, independently to decide in which direction it points. So the edge between 1 and 2 points at vertex 1 after this orientation. And then I'm interested in the number of sources, so the number of vertices with no edges pointing at them. This is, for example, the vertex 2 here and the vertex 4, and they are alternatively characterized that the number of edges pointing at them is 0, in other words, that their indegree is 0 there. Good, so back to the LLM. So I'm interested let's tell what this is about. I'm interested in investigating the random variable, which is the number of sources in a randomly oriented graph. So I start with a connected graph with no double edge, and I orient all of the edges randomly by fair independent coin flip, and I'm looking at the number of sources in the resulting graph. Setup notation and setting. Let's fix this. A simple graph. Starts enthusiastically thinking about this. Let's look a bit at what it's actually doing. And then it talks about that you can investigate expectation variance and the generating function. And the key point is that being a source is a local event, but actually it's only local if you look at a single vertex. It becomes a bit tricky if you look at two neighboring vertices. For example, they cannot be both sources. So there we have to think about how to get traction in this problem. And one way to think about it is looking at the vertices with even in degree. I will detail this in a moment. But let's finish setting up the problem. Not supposed to work too hard here, so maybe I just stop it for a second and get the answer now. It defines what the source is. All edges incident to V point away from V. And then it marginally gets the nice thing that the probability to be a source is essentially all the edges have to point away from us. And then the total number of sources you can write as indicator over the vertices, and there you get a first result that the expectation is easy. You just get right away what the expectation is, but the dependence is a bit tricky. So it says this already nicely, and it also says what I told you, and the variance is also a bit tricky. And then it can find the exact distribution, but this is tricky, and now we have to give it some idea. So in general, the LLM is good at working out things, but it is still a bit restricted on having a big picture and generating new ideas. So let's see. The sources is a bit tricky. Let's first look at an easier problem. Let's look at all the vertices which have even in degree, and let's identify their distribution. The distribution of their number. So this is a bit brutal bound, because essentially what I'm saying is it's very difficult to say if the in-degree is 0, but 0 is a special case of even. So let's look at the number of cases where the in-degree is even first. It can, of course, be a very bad bound. For example, if you bound the number of zeros in the natural number by the number of even numbers, then that's not very satisfying. But the bound can produce interesting results in the case where the degree is not too large. So let's see if it can figure out the joint distribution marginally. The parity of the in-degree is just a Bernoulli random variable. But globally there's a constraint. And yeah, it actually managed to get the right distribution. I recognize this formula. This is a binomial random variable conditional on that the outcome is either even or odd. So it says x is distributed as a binomial random variable conditioned to have the parity n and m are the number of vertices and number of edges. Okay, and it has a proof. It just fixes one orientation. And another orientation is obtained by reversing some subset of the edges. Okay, there's a different proof than the one we discovered. But I think this is also a possible way to do it. I'll think a bit more about this in a moment. Now we can, of course, upper bound the number of sources by the number of even in degree vertices and get a stochastic domination result. But we can also lower bound the number of sources by something which depends on the even in degree vertices by using the directed handshaking lemma. So let's have it working, and in the meantime we discuss what the directed handshaking lemma is. So if you look at this graph, if you have a graph, let's start with no edges and just vertices, and you start adding edges to the graph, then for every edge you add, you will increase the in-degree of a vertex by 1 and the out-degree of another vertex by 1. So the sum over the in-degree and out-degrees has to correspond to the number of edges. Okay, so it says there is a pointwise lower bound. So sources have in-degree 0, this is the basic bound. And now it applies the directed handshaking lemma to find a relationship. And the way to think about it is that the handshaking lemma, let's have it work, and then we can look at some formulas while discussing how a possible proof could look like. Okay, so it found the right formula. So if I divide the number of edges by 2 and correct for the number of vertices minus the number of edges, then I get a lower bound for the sources. Let's see a bit why this is the case. So you split the vertices into 3 classes. The sources have in-degree 0. If they're even and no source, the in-degree is at least 2, and if they're odd, the in-degree is at least 1. So if you look at the handshaking lemma, then you get a lower bound for the sum on the right-hand side. Remember, the handshaking lemma relates the number of edges to a sum over the in-degrees, and then on the right-hand side, the sum is lower bound. The sources contribute nothing. The odd parity vertices contribute at least 1 times their number, and the even contribute at least 2 times their number minus the sources. And then you solve, and then you get a nice bound, and there we are. This is correct. And now we have almost surely that S is larger than L, where these are 2 random variables. Then it talks a bit about expectation. That's not so useful. And what's more interesting is probabilities. Okay, it speculates if you can actually do something more there, but let's do something else first. I want you to look at whether these bounds are sharp, especially if the lower bound is sharp in graphs with restricted degree. Bounds. So let's see what it's doing. Okay, it finds something for maximum degrees 2. I think you should also find something in trees. Let's see how this is going. On a line graph, it's very easy. On a line graph, so if you have 2 edges pointing at each other to create a sink, and then you continue, then at some point you will have to have a source as well if you ever want to change direction of the edges. Etc. But in a tree, they should also get a result, because I remember that ChatGPT told me that you have these three classes and the sources, the odd degree, and the in degree at least 2. And I think on the tree, This might also work nicely. So let's see. Okay, it's still optimistic for the degree 3 case. Interesting. It's of course nice if you have the feeling that the LLM enjoys what you're asking for. So it looks at some examples. So for example, a star graph is a good example to look at, because you have one vertex with an exceptionally high degree and all other vertices have degree 1. So this is a good candidate for counterexample. And so it looks at the defect in our formula. It's a bit strange that it talks about the indegree of vertices, because that's random. I would have expected to talk about the degree of vertices. So bound, yeah, with restricted degree, I meant bounded maximum degree. So it has the exact formula for the defect of our bound, and it involves a sum over the vertices which are odd and have more than 3, and or even which have more than 4. Okay, so it has figured out how the bound relates given the actual orientation you have. Okay, so that's actually nice. So in the defect in the maximum degree 2 case is exactly the random number of indegrees vertices. So that's if all. Good. I think I'm happy with that. So then let's wrap it up. So I would like to talk a bit about the interpretation of this result for mathematical text. It is as important that the result is correct as that one tells a story which is related to it. So what is the story related to our result? So I'm priming it a bit to not just produce a document with formulas, but somehow explain why this is interesting and what's I think it has an angle on it, so it says we find the right intermediary at a random variable. It's nonlinear and local problem, and you find a easier upper bound. Okay, I can read this when it has produced the final text. Okay, right story. So then please produce a LaTeX document for me to download with the result we have, explaining to the reader and the corresponding story. And let's add with proof and lemma, so then it knows how it should look like. And let's look how it's going. It's a bit tricky. Sometimes it has an easier time producing the LaTeX as an answer and not operating on a text file. But I think in this case the scope is still something it can handle in one go. And then we look at the Okay, so we have our paper. So let's look at it. So it has a document, parity, sources, and in-degree bounds in random orientations. So we record a short chain of observation about random orientations of a fixed connected sample graph. The original quantity of interest is the number of sources. We pass through the easier variable counting vertices of even-indegree, which law we can completely determine by parity. We then use the directed handshaking lemma to transfer this information back to the source count, obtaining a deterministic lower bound. Finally, we identify the exact effect in that bound and show that it vanishes identically for graphs of maximum degree at most 2. This is exactly what we expected. So it starts with a connected simple graph, n vertices, m edges. Orient each edge independently and uniformly at random, and look at the corresponding random variable as the number of sources or 0-in-degree vertices. So this variable is rigid and nonlinear, difficult to describe, and says a vertex is a source only when all incident edges point outward, and a more tractable statistics is the even-in-degree vertices number. That linearizes the problem, that's the right conclusion. And then if you just change one edge, then you toggle the in-degree parity at exactly 2 endpoints. And that's the only global obstruction. That's also correct. So then it obtains this lemma that you have this constraint from the handshaking lemma on the global variable, and then you get this little result. Let me see how that is proved. It's talking about the vector of parities, and that's a uniform random variable in this subspace. And why is it uniform? It fixes the reference orientation, and then it flips an edge and then argues that this introduces a symmetry. I have to think a bit, but I think this can be a valid argument. And then it goes to the next thing and gets the proposition where we have the deterministic sandwich for the sources upper bounded by the even-in-degree vertices. As I said, 0 is a special case of even, but we also get a lower bound from the handshaking lemma, and it has a nice proof where it looks at these budget constraints in the handshaking lemma. And then you solve and you get this formula here. And then it computes the exact defect. You get no defect in the case where you have a maximum degree of 2, and then for so you have the range where this is sharp on paths and cycles. And then for subcubic graphs, you get this additional defect where the in-degree 3 vertices mess up your bound a bit. And then the story, so the original variable is difficult. Passing to parity gives a linear shadow of the orientation encoded by the parity vector that is conditional uniform, and you end up with a binomial distribution conditioned on the parity. And then the directed handshaking lemma gives the quantitative statement. Good. I think I'm happy with that. I will share the document just for the curious of you and finish with a thank you.